in our youngest kid's room somewhere. I don't know how or whatever, but he found it.
Probably picked it up off your...
Yeah, I don't know what happened, but
It's shiny.
I probably had it in my pocket for some reason. You know, I take it off sometimes, and I probably lay down to read him a book, and it fell out. But I'm going to save that paper clip one in case I need it later.
Oh, you made a paper one too?
Paper clip.
Yeah.
Oh yeah. My daughter made me a paper one. It's great, huh? It lasted like 6 hours.
Yeah, but that's pretty good. Okay, so the second test is tomorrow. Exam 2 tomorrow. And the topics are everything up through principal stresses. Okay? And strain is listed before principal stresses, right? So including strain and constitutive relationship and including principal stresses. And then today, I'd be happy to answer any questions you have, and then once we get past that, we'll move on to the next topic that won't be on the test. One thing I want to say about the test, too, I think I didn't make this clear to people. I thought I'd mentioned it before, but I know a few people I mentioned this to. It was like a revelation, game changer. So if you don't have a calculator that does eigenvalues and eigenvectors, or if you can't figure out how to multiply those matrices or whatever, do it on a laptop. You can do it in MATLAB if you have MATLAB on your computer, but you can also just go to Wolframalpha. And if you go to Wolframalpha, go to the search thing, type in so Wolframalpha, and search for eigenvector calculator. It takes you to a page where you enter in the elements of the matrix you want, click go or whatever, and it gives you the eigenvalues and the corresponding eigenvectors, and that's fine. You can use that on the test and everything. Okay? So no need to compute eigenvalues or eigenvectors by hand. Okay? Be sure that you figure out how to use it. If you're going to do that tomorrow, be sure you figure out how to do it before you come to the test, because you just have to make sense out of the syntax and stuff. You don't want to do that during the test. It's not hard, but just make sure you understand how to do it before. Okay. Any questions about the test? Any questions about homework problems? Yep.
Can we do number 5 on principal stress?
Yeah, can someone loan me the assignment? Yeah, that's good. Points.
Number 5.
So it gives a stress tensor of negative 23.26, 4.822, 0, 4.822, negative 11.76. Oh, that's not even a stress tensor. That's not symmetric. You got to make it symmetric.
It's number 6, I think.
Oh, that's 6, yeah.
I think you want 5.
Okay. I'm not, yeah, I'm doing the wrong one. Number 5, negative 6.1852, 0, negative 2.2504, and then 0, negative 12, 0, negative 2.2504, 0, negative 0.8187, and that's in megapascals. So first draw the stress element, then calculate the principal stresses, give the principal stress tensor in a coordinate system that you draw, calculate the strain, maximum shear stress, that kind of stuff. All these problems are the same. So the stress element, you have the XX stress of 6.1852 pointing in, it's in compression. And then in the Z direction, you have a component of 2.2504 pointing backwards. In the Y direction, you have just this, 12 in compression. And for Z, you have 2.2504 pointing to the left, and compression again of 0.8187. Okay, so there's the stress element. So now let's do this in Wolframalpha. Okay, so Wolframalpha, it does everything. I haven't used it that much, but I know it solves differential equations and all this crazy stuff. So search for eigenvector calculator. And it shows you the format of the matrix that you need to enter. It's basically the same as the format of a TI calculator, except you use squiggly brackets instead of square brackets. The way it's entered right here is the matrix that's shown below. So I'm going to go in here and edit the first row. So the first row for number 5 is negative 6.1852, comma 0, comma negative 2.2504. And then the second row is 0, negative 12, 0. And then the third row is negative 2.2504, 0, negative 0.8187. All right, so now that matrix is entered. Hit enter to calculate it. And so this is the original matrix I entered in. And what we get out so it lists the eigenvectors here, and it lists the corresponding eigenvalues here. It chose its own, it had its own way of choosing the x, y, and z coordinates. They don't line up very closely with the old x, y, and z. That's fine. You can just use theirs. I guess we need to make sure. I assume they're giving us these eigenvectors in a coordinate system that's right-handed. But we can make sure. Basically, what we have is our old y-axis is the 1. Our old x-axis is the 2. And our old negative z-axis is the 3. So y cross, yeah. So this is, we can just use this as V1 is our x-axis, V2 is our y-axis, V3 is our z-axis. So let me draw these. Our coordinate system, well, let me write out the values first. So sigma 1 is negative 12, and that corresponds to 0, 1, 0. Sigma 2,
Lambda or sigma?
it is lambda, yep. Lambda 2 is equal to negative 7, basically. And that corresponds to 0.9400, 0.342. And then lambda 3 is 0, and that corresponds to 0.342, 0, negative 0.940. So as a coordinate system, if we draw this, there's the y-axis. Yes?
When do I get to say it's 0? It's actually 0.0, times 10 to the negative 5 or something like that. Let's start around that.
Let's round to,
When do we get to say that? Is it negative 10 to the negative?
round to 2 decimal places, 3 decimal places, something like that. But I don't really care. You could write that whole thing, Yes? Which one? V2. Why is it negative 7? V2? This? When you entered it in? I guess it just gave you a different set. Remember, there's different possibilities for how this will work, and they're all equivalent. So that's weird, though, that it did it differently for you than it did for me. But okay, and then we have the x-axis going that way. Oh, no, I'm confusing myself. This is the x-axis, the new x-axis. This is the new y-axis. And this is the new z-axis pointing back.
How did you figure that out?
So this is our starting coordinate system. Well, not like that, like this. There's x, there's our old x, old y, old z. And then I just used the components of these eigenvectors, like tried to represent what those vectors would look like. Each one of those is an axis of the new coordinate system. So the vector 0, 1, 0 is the x-axis. That looks like this. It's just in the old y direction.
Because the 0
Yeah. The new y-axis is 0.940 in the x direction, 0 in the y direction, in the old y direction, 0.342 in the old z direction. So that's this. So I'm just plotting out those points.
So that would be different if you had lambda 1 equal -7, right? Then your coordinate system would be.
Then it would be a different coordinate system, yes.
And it doesn't matter which way you do it.
Right. But the way you draw the coordinate system needs to match up with the order of the eigenvalues.
So so my question is, on your z-axis, your new z-axis, 0.342 is over in the x direction, 0 in the y direction, and then you just, how'd you get the z to look like that? Totally different looking on yours. Oh, no, I stand corrected. Which one is?
Okay, so which one are we talking about? The new y or the new z?
The new, let's see, I'm trying to remember. My eigenvalues come out different as well.
Very different.
Negatives. What's going on here?
Mine are negatives for the
Eigenvalues, or the vectors.
for the vectors. They can be negative because remember each one can be, this could be 0, 1, 0 or 0, negative 1, 0.
Oh, yeah.
This could be negative 0.940. Okay, and then you just have to choose 3. Each axis has 2 possibilities, and you just have to choose a set of 3 that satisfy the cross product requirements for a right-handed coordinate system.
So if we use a calculator like that, is that going to be guaranteed, or we still got to?
You got to make,
Look.
I think my calculator does not give you necessarily a right-handed coordinate system, so you have to be careful.
One of them's goofy like that. Yeah, I don't even know what it's. Okay. I mean.
Yep.
So when you picked like lambda 1, 2, and 3 for x, y, and z,
Yeah.
did you just pick that?
I just did it in the order it gave it to me.
So is that an assumption that's safe to make, or do you?
Yeah, that's safe to make, but it's possible, depending on how the eigenvectors are calculated, that you might have to switch the signs of one of these eigenvectors.
Okay.
Yep.
Okay, so then could lambda 1 be z, and if the lambda 2 and 3 are x and y, and we still cross?
Yeah, if you called, all that's required is that this eigenvalue of negative 12 corresponds to 0, 1, 0, or 0, negative 1, 0. You can call that your x-axis or your y-axis or your z-axis. Yep.
So when we put the 3 eigenvectors together, does it have to make a symmetric matrix? Does that matter?
It's not going to make a symmetric matrix. So it won't be symmetric. In general, it won't. In the examples I give, it will be, it'll look sort of like it has symmetry, but that's just because of the examples I do are in the plane. In general, it won't be. Any other questions about that? Okay, so now the new principal stress tensor is, I'm calling this negative 12. I'm saying that corresponds to our x-axis. Negative 7 corresponds to our y-axis. And 0 corresponds to our z-axis. Yep.
So we could all have different answers for the principal stress vector, depending on what order it is.
Yeah. So you could also get, I can't do in my head right now how many permutations there are, but there are a lot because I think, well, let's see. I can't do it in my head right now, but there's a bunch. Yep. Okay, so here's a brain teaser. How did I get so lucky when I made up that crazy matrix, that I came up with -12, -7, and 0 as my eigenvalues. You know? How did I come up with that first stress tensor that gave round numbers for...
You inverted it?
I went backwards. Yeah, so what I did was I started with this matrix, and then I did a coordinate system transformation of that stress tensor of 20 degrees about the y-axis. And that gave me this jumbled up version of the stress tensor, and then that's what I gave as the question.
That's why you need a PhD.
Just that. That's what I did at my defense. They're like, whoa. And then the strain and stuff. So I think maybe I won't do that here. But so then you just, the Voigt version of the principal stress is -12, -7, 0, 0, 0, 0. And so then the Voigt strain is the compliance matrix times that Voigt stress. Any other questions on here? Like, all these problems are pretty similar to each other, but I'd be happy to go through another one. Yep. That's the 6 by 6. It was given in that problem. Yeah. So Young's modulus was 200 times 10 to the 9. That's Pascal's. Poisson's ratio was 0.3. And those represent a type of steel. This is megapascals. Oh, this is an easy mistake to make. And maybe I would have just made this mistake here. These values were given in megapascals, and so they're in megapascals here. So if your Young's modulus is in pascals, you need to represent that stress in pascals too. So before you do this multiplication, this should be -12 times 10 to the 6, -7 times 10 to the 6. If you don't do that, you're going to get strains that are a million times too small. And that's a lot of error. It's hard to overlook those factors of a million.
No, it was zeros. I see how you did that now. So because I've seen it in some of the homework, when you're bouncing between megapascals, and then when you're bouncing between your, how you represent your numbers, then it changes. When we see it,
oh yeah,
go back and check, like, how did he get that?
Yeah.
It should have like the exact same thing.
yeah.
Because there was just no multiplication by 10 to the 6 on your eigenvector, which we did it in those values.
Yeah, for your eigenvalues and eigenvectors, it doesn't come into it. Okay. But at the end, you just have to remember that you're doing it all in terms of megapascals.
Right.
It matters when you multiply by the compliance matrix because that has other units in it. So you have to make sure the units match.
Could you just convert your Young's modulus and not have to convert all the other numbers?
Yes. Yep. So you could do the whole thing in megapascals. You just have to remember then that the Young's modulus is 200 times 10 to the 3rd megapascals. Six? Okay. Yeah. So 6. Well, you got to make that matrix symmetric. to start with. Doesn't make any sense like that. So the stress tensor, we'll start with negative 23.26, 4.822, 0, 4.822, negative 11.76, 5, and then the last row has to be 0, 5, 0. You have to change this one so it's symmetric with that one. Okay, so when you do
How many points is this homework out of?
I haven't thought about that yet. 6 per problem I grade, it'll be 6 points. You know what I mean? Yep.
What percent of the total grade is homework?
20%.
20?
It's huge. It's too much.
No, that's good.
I mean, the homework grades tend to be really good. You know, the quiz grades tend to be sort of low. The quizzes are kind of hard, but it's kind of made up for by the homework grades that are usually pretty good, you know. Okay, what am I doing? Number 6, negative 23.26, 4.822, 0.
If we come across in further homeworks and problems, to make stress tensor like this, or there's a 0 or there should be a value, and there is a value in the to make it symmetric, and just make a note to you.
Yeah, that would be great. And anytime anybody finds a mistake like that and is near a computer and feels like sending me an email about it, I would love to have a record of that stuff so I can go back and fix it, you know. Otherwise, it'll just happen again next semester, and then I'll be like, oh, yeah, I remember that. 4.822, negative 11.76, 5. And then 0, 5, 0. Oops. Oops. Okay.
Should watch Planet
Right now.
Yeah.
It's a good idea. Okay, so lambda 1 is negative 25.14, and that corresponds to an axis of 0.929, negative 0.362, 0.072. Then lambda 2 is equal to negative 11.84, and that corresponds to an axis of 0.362, 0.859, negative 0.363. And then the last one, lambda 3, is 1.95, and that corresponds to 0.069, 0.363, 0.929. So this time the coordinate system it gave me was pretty much in line with the original coordinate system. But if you plot those vectors in 3D, you can see the orientation of the new coordinate system relative to the old one. So if this is the old one, our new x-axis is mostly in the x direction, but a little in the negative y direction. So it goes out here and then a little bit down this way. That's our new x-axis. And then the second one is mostly in the y direction, but a little in the positive x and a little in the negative z. So that's over here somewhere. And the third one is mostly in the z direction, but a little in the positive x direction. So like that, something like that. It's pretty hard to draw in 3D convincingly, but and in that coordinate system, the stress tensor is negative 25.14, negative 11.84, and then the last one, the z, is 1.95. Oh, I forgot to, with the last one, I didn't calculate the maximum shear stress. What axis would you rotate about to get the stress tensor with the maximum shear stress?
The negative 11.8.
That's right. So the way I have it written, that's the y-axis. So if you rotate, yep, rotate 45 degrees about the y-axis for the stress tensor with the maximum shear. So yeah, you find the middle of the three eigenvalues. Sometimes if they're all negative, then the middle one's going to be negative, you know, but you just find the middle of those three and then rotate 45 degrees around that axis. So the middle one is negative 11.84. That corresponds to what we're calling the y-axis, so we're going to rotate this 45 degrees around the y-axis. And the value of what we would get is easy to find. The maximum shear stress is the maximum principal stress. What's the maximum principal stress? You guys learned maximums yet?
25.
That's, be careful about that. So,
So it's not absolute value.
right. Yeah, so it's the true maximum. So it's 1.95 and then minus the min. So, I mean, I guess all it would do is switch the sign of your maximum shear, which isn't really a big deal, but So 1.95 minus 25.14 divided by 2. So what do you get for 27.09 divided by 2? 13.54. And then you check and see if that material can handle a shear stress of 13.54. And if it can, you're feeling good. And if it can't, you want to redesign the system. Any questions about that one? Any other questions from the homework? Okay. Well, the next thing we're going to do is, who did I take this from? You? Oh, that's right. So now we're going to go into the rest of the class. Calculating. And I suppose it's probably worthwhile to say, I mean, everything we've done so far is true, undeniably. It's totally correct. From now on, everything we're going to learn is an approximation. Okay, it's based on assumptions and whatever, and sometimes it's good and sometimes it's bad. But so we're going to be approximating the stress occurring in actual bodies. And so we're going to break this up into different categories. We're going to start out by thinking about bodies that are loaded qualitatively the same way as the stress element. That's the easiest one. So the first category I call it bodies loaded like stress elements. And so, for example, if you have, so say you have a rectangular body like this. Let's say it's 1.5 meters long. And 0.2 meters front to back. And 0.2 meters tall. And say that it's loaded by uniform distributed loads. I'm going to draw it in a different orientation. Let me give you the coordinate system first. So here's the coordinate system we're going to use. And if you look at it just straight on the front, the coordinate system looks like this. The y-axis is coming out towards us. And let's say we have a uniform distributed load acting on this side and an equal and opposite one on this side that has a total value of 20,000 newtons. And then we have distributed loads on the top and bottom. That are given in terms of newtons per square area, newtons per area. So 10,000 newtons per meter squared and 10,000 newtons per meter squared. What's the stress tensor for points inside the body? For traction components, that aren't given in terms of a force per area, just divide the total force by the area of the loaded face. When you are given values in terms of a force per area, then you just use that value. So for traction components, given as force per area, just use that value. Okay, so the traction happening on the top face and the bottom face, those are already given in force per area, so we don't have to mess with those. The ones on the left and right, those are given as total forces, so we have to figure out the area of the loaded face and just divide. Oh, and I didn't say this explicitly. So what makes this a member that's loaded like a stress element? Well, the loading pattern just satisfies all the requirements of a stress element. You know, in a stress element, if you have, so if you have like a shear stress like this, you know you have to have a shear stress like this. If you have a shear stress like this, you know you have to have one like this. If the object has all of those same requirements met, then that's a member that's loaded following the rules of the stress element. Okay, and all you have to do is scale, like just the areas are different and stuff. So you just have to express all of those loads as forces per area, and then that's your stress. Okay, so on the ends, the normal traction is 20,000 divided by the area of that loaded face is 0.2 times 0.2. And so that's equal to 500,000 pascals. And so if I redraw this, we have this uniform distributed load on this side that's equal to 500,000 pascals. Equal and opposite on the other side. On the top, we have a uniform distributed load that's equal to, that was already given, so that's pretty little, 10,000 newtons per meter squared. And on the bottom, we have the equal and opposite. And so at each point inside, the stress element looks like this. $500,000 pascals in the XX direction. Shoot, you got to go back and change this picture a little. I missed the fact that for this to meet the requirements of a stress tensor, these tractions along the top and bottom have to have equivalent tractions here and here. Right? If this is a stress element, so we also have tractions on these two sides, like this. Okay, so then we have that. This is 10,000. This one's 10,000. And so now that's it. The stress tensors are all equal to 500,000. 10,000, 0, 10,000, 0, 0, 0, 0, 0. Okay, so if you're lucky enough to be dealing with a body that's loaded according to the rules of stress elements, then all you have to do is for each load figure out what the force is per area, and then that gives you the values for the stress element. That gives you the values for the stress tensor. The most common case where this is useful is for bodies in tension and compression. You don't very often get these where they meet the requirements of shear stresses, but you pretty often do get things that are just in tension or compression, so they have equal and opposite forces on the two ends. Any questions about, anybody want to clarify what I'm talking about here?
Yes, can you go up to the original picture of the, when you had to add those other forces?
Yeah, so that just, if those were not there, then we could not do this problem this way.
So do those forces go in the same, I would think they would go all like clockwise, no?
Nope, because if they all went clockwise, it would make that thing spin.
Oh, okay, yep, okay.
So they have to have this relationship in order to satisfy the rotational equation, the moment equation. Okay, so let's do an example that's in pure tension. So say you have a round cross section and this object has a length of 0.1 meters. The cross-sectional area has a radius of 0.01 meters. And I guess this is actually in compression, not tension, but you would treat it the same way. So let's say we have a uniform distributed load on the two sides of 5,000 newtons. And we want to calculate the stress tensor. Well, we have to take this 5,000 Newton force and represent it as a force per area. This meets the requirements of a stress element because the face at the top has an equal and opposite traction to the face on the bottom, and there's no shears. It's only normal stresses. So this traction, force per area, is equal to $5,000. Well, let me leave the negative off for now. So 5,000 divided by the area of the loaded face. The loaded face has an area of pi times 0.01 squared. And that gives you a value of 1.59 times 10 to the 7 pascals. So now you can think about this thing as having a distributed load acting on both sides of 1.59 times 10 to the 7. And if we think of the coordinate system this way, that corresponds to a stress element like this. And so the stress tensor is 0, 0, 0, 0, 1.59 times 10 to the 7, 0, and then 0, 0, 0 pascals. Yep.
Would that be a negative 1.59?
Yes, negative. You can see it once you draw the stress tensor, but also you know it's in compression, so it needs to be negative. How would you rotate the coordinate system to get a stress tensor with a maximum shear stress? What would you rotate? You'd rotate it 45 degrees around one axis. Which axis would you use?
Either X or Z.
That's right. You have two options here, the X or the Z. And what you would get is a face that's oriented at 45 degrees like this, or the reverse of that. And like I said before, for a brittle element that's loaded in compression like this, when it broke, you would get a break along that 45-degree line because that's where you have the maximum shear. Okay, one more thing about this. What if this member was loaded with point forces rather than with uniform distributed loads? Okay, so let's say that instead it looks like this. Oops, going the other way. 5,000, 5,000. Can you say anything about the stress in this case?
Yes.
Yes.
We're going to take away the
Yes.
somebody's
Saint Venant.
St. Venant's theory, that distance L, and then we'll just do
That's exactly right. So what we'll do here is treat it like it's a uniform distributed load. So 1.59 times 10 to the 7 pascals. 1.59 times 10 to the 7 pascals. Go through the whole calculation. Get a stress tensor that's equal to 0, 0, 0, 0, negative 1.59 times 10 to the 7, 0, 0, 0, 0. And then just ignore those results near the ends, near where those loads are occurring. Near the loaded ends. So those results are still good. They're just not good here or here. Any questions about that? Okay, and so one kind of problem that we're going to do now is, since now we have a way to calculate stresses in members that are in pure tension or compression, we can work on problems involving trusses, because every member of a truss is in pure tension or compression. Solve the truss, and then use this approach to figure out the stresses in the beams that make up the truss. Okay, so we'll do an example like that after break. So come back at 2:12, 2:13, and we'll start again. Okay.
Not my fault. Not my fault. Boom. You get the exact same thing I did, except for that middle value, which is 0. I got it. You got it. Freaking out.
I'm recording. Sure. Yeah, sure. Yep. Okay, so let's say we have this set up like this. Each of these two beams is 1 meter long. And we apply a force to the pin of 5,000 newtons. Each of these two bodies is a two-force member. Okay, there's a force where it connects with the wall, and a force where they connect to each other at the pin and where that force is applied. And that means, so every member is a two-force member. So the only possibilities are this or this. Okay, and the people who took statics from me do this differently than the people who took statics somewhere else. But take a minute and see if you can remember how to work through just calculating the external loads on these bodies first. And then we'll go in and figure out what the stresses are. Let's say that the cross-sectional area is 0.005 meters squared. Okay. So yeah, take a minute, see if you can remember how to calculate the external loads on these members. Feel free to ask me if you get stuck. I know most people haven't done this for a while. Talk to each other about it, but if you took statics from me, you might want to talk to someone else who took statics from me, and vice versa, because it's a little different. So first I'm going to do it the full way that we did it in statics. The people who took statics other places didn't do it this way. I'll do it that way after. But so this is definitely like a longer way to do it for problems like this. For problems like this, treating it as a truss specifically gives you a pretty good advantage in numbers of equations and stuff. But I'll call the top member, member 1, joints A, B, and C. And we're going to assume, like we did in statics, we're going to assume that the pin connecting members, we're always going to lump that in with the lowest numbered member at that joint. Okay, so at the pin B, we're going to lump that in with member 1 because joint B connects 1 and 2, and 1 is the lowest numbered member. Okay. So I'll do a free body diagram of member 1. There's a force vector here of RA. There's a force vector here of the force on 1 by 2. And then that 5,000 newtons is applied to the pin, which we're treating it like it's part of member 1. So there's the complete free body diagram. And now write out the table. Pancake, artist, row, 4, marzipan. And now we have to choose an about point. Doesn't matter where you choose it. I guess I'll choose it. I'm going to make the about point here. So first there's this force vector F12. I'm going to go straight into just calculating the row vector. The row vector always goes from the about point to the force that you're interested in. So this force F12 has no row vector. The force vector is F12x, F12y. And take the cross product and you get no moment. Then the 5,000 Newton, that has a row vector of 0. The force vector is negative 5,000, 0. No moment. And then the force RA, this is the row vector from the about point to the point A. And that vector is negative 0.342, positive 0.940. The force vector is RAX, RAY. And so the moment is negative 0.342 RAY minus 0.940 RAX. Okay, so you get three equations. The first is from summing up the x components of the forces and setting them equal to 0. And so you get F12x plus RAX plus 5,000 equals 0. I'll write that as is equal to, or plus negative 5,000 is equal to 0. If you move that over to the other side, you get plus 5,000 there. The second equation says F12y plus RAY is equal to 0. And the third equation says negative 0.940 RAX minus 0.342 RAY is equal to 0. So there's the first three equations. Any questions about that one? And now we'll go to the second body. Down here we have a force vector, I'll call it RC. Here we have the force on 2 by 1, which is negative force on 1 by 2. And what about that 5,000? Nope, that 5,000, we've already used that. That's acting at the pin, which is part of member 1. So this is the complete free body diagram here. And so just like with the other one, I'm going to skip filling in P and A. You can write the coordinates of these points and do the subtraction and get rho. I'm just going to go right to rho. So first, I'll put the about point down here at C. So for that force RC, the rho vector is 0, 0. The force vector is RC, x and y. And so the moment's 0. And now the rho vector goes from the about point to the force that you're looking at. So now when we're going to this force negative F12, the rho vector is positive 0.342, positive 0.940. The The force vector is negative F12x, negative F12y. And the cross product is negative 0.342 F12y plus 0.940 F12x. And we get three more equations. Equation 4 says negative F12x plus RCX equals 0. Equation 5 says negative F12y plus RCY equals 0. And equation 6 says 0.940 F12x minus 0.342 F12y is equal to 0. So now we have 6 equations for 6 variables. We can solve this with a matrix. So 6 equations. One, two, three, 4, 5, 6. Yikes. And then 6 variables. I'll call those F12x, F12y, RAX, RAY, RCX, RCY. Okay, so equation 1 says F12x we have 1, RAX we have 1, and the constant is 5,000. Equation 2 says F12y we have 1, RAY we have 1, the constant is 0. Equation 3 says RAX we have negative 0.94, RAY we have negative 0.342. And the constant is 0. Then equation 4, F12x we have negative 1, RCX we have 1, constant is 0. Equation 5, F12y we have negative 1, RCY we have 1, constant is 0. Equation 6, F12x we have 0.94, F12y we have negative 0.342, and the constant is 0. Can someone reduce row echelon form that? Yes, that's right. And nothing else anywhere?
I got numbers.
Okay.
A lot of them.
Okay, good.
All right. So for F12x, I got 2,500. For F12,
Okay, wait. 2,500, okay.
for F12, I got 6871.25.
Okay.
For RAX, I got 2,500.
Okay. Okay.
And then the third one is 2,500. 6871.25. I don't know if we put that in there, so.
Okay. Anyone else get numbers?
I got the same.
Okay, good. All right, so what we got here is on member 1, we have this force vector 2,500, negative 6871.35. At the other end, we have 2,500, 6871.35, plus that 5,000 Newton vector in the negative x direction. So when you add those two up, you get negative 2,500, positive 6871.35. And then for the other member, you get down here at C, 2,500, 6871.35. And here you get negative F12, so negative 2,500, negative 6871.35. Okay, so if you use inverse tangent to figure out the angles these are acting at, what you get is that both of these two members are in compression, and the magnitude of that compression is 2,500 squared plus 6871.35 squared square root. And what's that equal to? Just the magnitude of that force is the value of compression. How do you know it's compression and not tension? You can tell by the directions of those components. Up here, it's being pushed this way and this way. So that's a vector pointing straight that direction. This is opposite, so it's like that. Same thing over here. This one is going exactly that way. This one's going exactly that way, so it's compression. And what's the magnitude?
7312.
Okay, 7312. So for both of these, what we have is 7312 acting on each end. So now I'm going to do it the way that you do it if you recognize that these are two force members and you don't have extra time. You gotta get this done so you can, get to First Avenue or whatever for Danceteria Friday or whatever. So then you say, so what if you recognize that these are two force members? Then you can treat each of them like a cable. It's like a cable, but where the tension can be positive or negative. And isolate the pins as particles. Okay, so let's isolate this pin B. what forces are acting. There's a 5,000 Newton force to the left. And now we'll treat each of these two members like they're just applying cable tension to this pin. So one goes this way, I'll call that F1. And one goes this way, I'll call it F2. And we're going to solve for F1 and F2. If we get a positive value, it means the member's in tension. If we get a negative value, it means the member's in compression. We need to come up with unit vectors for both of those. A unit vector for this force F1, representing its direction, is negative 0.342, positive 0.940. And then we multiply that unit vector by the value F1 to get the force vector. For this F2, the unit vector is negative 0.342, negative 0.940, and multiply those by F2. And then the third force is the negative 5,000, 0. Add those up and they have to be equal to 0. That's Newton's second law. And so you get a system. Your two equations are negative 0.342 F1 minus 0.342 F2 is equal to 5,000. And your second equation, 0.940 F1 minus 0.940 F2 is equal to 0. Okay, so F1 is equal to F2. And so that says negative 0.684 F1 is equal to 5,000. So F1 is equal to F2. What's 5,000 divided by 0.684? Hopefully 70, whatever, 12 we got before.
So 73.
Okay. Negative 7310. The negative says compression. Okay, so both of those two ways give the same answer. Obviously, in this case, using that truss simplification is, way, way faster. But you can't use it for everything. That's the downside. You have to have sort of piecemeal approaches to every structure that you encounter. So that's the downside. Anyways, so now we have this. Let's just quick do the calculate the stress. So if this is the coordinate system, the XX stress is equal to negative 7310 divided by the cross-sectional area, which I think I gave as 0.005 meters squared. What do you get if you divide 7310 by 0.005?
1.46 e to the 6.
Okay, 1.46 times 10 to the 6 pascals.
That'd be a negative.
Negative, yep, you're right. So the stress element looks like this. And the stress tensor looks like this. Negative 1.46 times 10 to the 6, and zeros everywhere else. Any questions about that? Okay, that's all.